All right, you are welcome to day two of Python for Civil Engineering and Water Resources Management. So the last time we discussed, we stopped at this equation, and today we need to find V2 in terms of V1. We know from from the question that Q1 is equals to Q2, and Q is given as AV is equals to BH multiplied by V. So assuming that B is equals to 1, okay, so we write the equation of this symbol of V using the SymPy uh, library. Then our equation 2 becomes this B multiplied by H1 V1 and then comma B multiplied by H2 and V2. Then if you display that equation of this line 10, you have this, okay? Then you can substitute equation 1, in equation 1, you can substitute G with 9.81. When you do that, you'll get this return. And also in equation 2, when you substitute B with 1, you get this equation as well. So you can look at this and look at this. They are almost about the same thing, but with some substitutions being done. So B is equals to 1. You can see it becomes 1 here. And then B is equals to 1 here also becomes 4.5. Okay? Then when you now solve the equations, when you solve the equations, this is what you are going to arrive at. So this is the solution to the when you solve equation 1 and equation 2 together. All right. So you want to check what is the first equation and what is the second equation. This is what you are going to get. So for x in answer, which we have defined earlier here, this is our answer. So you can see it picked just the first one. So you have a list of two values here. So you have the whole of this as the first. Okay. Okay. All right. So you have this as the first, and then you have the second solution as this. All right. So 3.9, 3.9 like this. Okay. So that's the first solution. You have from this point -4, -2, this, and then this. Okay, so that is the solution of the equation you get. Now I want to introduce you to Python and NumPy. We have already done that. If you check one of my videos, I'll just run through this. It's another library that's very important for numerical Python working with arrays, so you don't have to be picking one value to work with. So if you do any computation, it cuts across all the array that you are working with. Okay, so we can create an array by saying numpy.array. Then you put list of values you want to convert into an array. So when you do that, you get these values. So also you can identify or pick any of those values that you want using the subsetting method. For example, I have a list of arrays between numpy 0 to 1000. Okay, so I'm creating values between 0 and 100, but I want 1000 values in between 0 and 100. So when I do that, I want to get the third value. The third value will also be 0. Okay, so it returns a float. Usually linspace returns a float. Okay, so you want to create a table also, a table of values for sine theta and cos theta. So we just create a simple linspace between 0 and pi. Okay, and we want only 12 values. So if you find the length of this theta, you're going to see length of theta is equal to 12. So that is what linspace does for you. It creates random values between the start, which is 0, and then the end, which is this, and the interval, so the in between values, you want up to 12. So you just pick the number you want. So easily you can create random arbitrary values that way. Okay, so for I in range of length of theta, okay, so we created 12 values, which is form of a list. So when you run to print each of the values, that's for I in range of length of theta. Length is going to return to you 12, right? Like we did here. So if there are 12 values and then theta is the original value, then it says print those values. Okay. So we have made this to two significant figures. That's why you see it this way. But theta is actually 3.142. So between 0 and 3.142, you have 12 values which was randomly created. Okay, so now we want to define our cos theta and sin theta. So we just put the values of theta into NumPy, that's the sin theta and cos theta. So when you do that, you discover that each of them have 12 values of length because we're using theta, which is from 0 to 3.142, but we have 12 values in between. Okay, so when you do that, you can convert that, you can create a table sort of by just printing theta, sin theta, and then using the tab to separate them. So what this means is that theta, sine, and cos are string formats, and they are going to form the title. And then for I in range of length of theta, print this. You show the theta I, 3 significant figure, sin theta, 3 significant figure, and then cos theta, 3 significant figures. So you can see the output looks very interesting to look at. You can copy this out and use, or you can even screenshot it and use as an image. That gives you the final output. Okay. Now, a simple library for plotting is called the Matplotlib. There are other ones like the SNSC bond. You can also use that for plotting. But for now, we are looking at the Matplotlib library. Okay. So you can simply say import matplotlib.pyplot as PLT. Okay, so this PLT is just plt.grid is initialization of the plotting function. So we want to plot theta and cos theta. So usually in Matplotlib you use x and y. Okay, for simple two-dimensional data sets. For example, x and y. Okay, so we're assuming that our theta is our x and our sin theta is the y. So we label the sin theta this, and then the color of the line we want is k. And then the second line will be for cos theta. Okay, you can see it's labeled cos theta. So we want to draw a continuous line over sin theta and cos theta. Okay, so when you plot plt.scatter gives you a scattered plot, just a dot 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 dot. Okay, while plt.plot only gives you a continuous line. Okay, so that's the way you plot a line, and scatter is how you plot dots. Okay, scatter plots sort of. So we're now plotting line and plot and dots along each point. So when you do your x you have redefined it as x is equal to this 1000 points. Okay, so we just added more points, though the data is not within all points, but we just want to show extra points. Okay, so never worry about that. That's lane space. It will give you a continuous line, a smooth line. Okay, so you can see lane space between this and 1000 still does not alter the function of this NumPy. I mean your theta that you're working with. So when you plot this, you have this color for sin theta is black. So you can see from the figure, you can see that you have sin theta as black and that. So we have another simulation problem here that we want to solve. Given a vertical section of hemispherical water tank, simulates water flow to find the total time it takes to empty the tank when input parameters H1, H2, R, C, D, G, and D are provided. So the symbols will take the usual meaning. So if you look at this diagram, the illustration is already given to us height 1, and this is height 1, this is height 2, and this is small h. Then this is the change in the height. Okay, so this is the radius. Okay, and then this is the orifice. Okay, so the algorithm actually needs us to make a function. The function helps you for repetitive purposes. Okay, you can repeat an activity over and over given the parameters that you have, instead of creating new functions or creating new things all the time. You can just use the same function and run through all your data sets. Okay, so what you first do is you create the function. Remember, we have talked about NumPy, and NumPy helps us to create an array. So we want to calculate the time elapsed for each step, and then the output will return a list of t and h. Okay, so time and height. So this is the formula we're going to use. And when we use that formula, we initialize the variables of time as 0, and h is equal to h1. So we create a new list here by doing this, and then the h list by doing this. Okay, so if h is while h is greater than h2, that is this h, if it is greater than h2, then the change in time is going to be this. Okay, and therefore Okay, so when you have this, so when you compute, you have 3.388513.2164. Okay, so the total time will give you that because we indicated in the function that it will print, it should print the total time, which is time like this. But you know, we're going to return a list, so it will have several items in that list. Okay, so when we now want to plot, we now plot our x-axis will be t list, that is the time, and then the height will be h list. So they will return the same number of values. So when you plot that by using the default PLT Matplotlib, a plt.grid, say to add all the grid points. Okay, these lines, vertical and horizontal lines. Okay, so your x label, you label it as time elapsed in seconds, and then your y label height in meters. So when you plot that, you can see it gives you this figure. Okay, so define empty analytically. So if we want to calculate the time required analytically, so when you create, plot that also using the direct equation, right? Without using all those other methods that we used earlier. So you also discover that you get the same total time. Okay, get the total time of 3 years, so which is about the same thing. So and now I want to add one more thing, how to process image. This is maybe useful for you. So you have an image of a building and you want to look at the cracks, you want to look at where exactly how the line of the cracks is all about. You want to reduce image, you want to add images, you want to put images inside your figures and inside your plot. So all you need to do is import NumPy as NP, import your Matplotlib, import your OS where necessary. So your image name, directory where that file is located is image2. So you just use the plt.imread, so to read the image for you. Okay, so when you print the image, it gives you this matrix, that is the size of the image and all the information about the image. So when you show the image, you can see now it's plotting it exactly this way. Okay, so it's bringing out the exact way the image is, and then gives you the dimension of the image. Okay, so you can reduce the dimension, you can crop, you can decide to say you want it cropped between 450 and 850. So this gives you your x, your y, and your z. So that's the dimension, your x, y, and your z. Okay, so you are cropping it and reducing the size. So when you reduce the size, see what you get. Okay, 0 to 300. Okay, but the everything inside the cracks remains the same. I mean, the dimension or the content of the figure remains the same. So you can also do channelization. Okay, so if you make everything 0, okay, you change the image, the shape of the image, and turn everything to 0, then you say from x, y, and z, only make your z1, and then say your image is to z, so you replace that with this. So what do you get as your new image? You get this green color. Okay, you can equally remove the color, say image greater than 100 multiplied by 255. Okay, so it removes the color and returns only this for you. All right, so more about this you can find in this reference, and let's look at this beam analysis. For this beam analysis, we want to plot the uh, some of the important aspects of this beam illustration using that equation. Okay, so we're going to look at all these things. So you can see I have a few things here to show you, and then we'll look at the beam balance, and then you know, every other thing that is associated. Now let's just go further and look at this one by one. So I would please don't forget to like, share, and subscribe. If you have any questions, you can ask me. I'll go through this code with you one by one, or if you need me at any time, I'm available. Okay. So we just have to define some of these parameters given, using this problem. So just define that we want the LP and the R and the Rx and then the Ry. So we want the x-axis of R and the y-axis of Y, and then the breadths. Okay, x, y, and then the breadth. So you define them as this so that the computer will understand when we come to the SymPy function. So having this done, you can make equations like this and display them. I've taught you also this, I've shown you this. Also, you can find the moment about A0. So that's the positive clockwise momentum. You can find that using this equation. And when you display those equations, at the end you find, RA of x is 0 minus p plus RA of y plus 1 is 0. LP over 2 minus L is equals to 0. Then the reaction you get is AY and RB, P over 2 and P over 2. Okay, so using the singularity function method, you have this X and you have L as symbol as it, and you make this constant equals to true. Okay, when you make this constant equals to true, it says that wherever you see L is a constant, it's not going to change. Okay, so it's going to assume that that's a function throughout. So make share expression. You make this expression this way: singularity function of x of this, and then sp of singularity function x of this. So we are using that singularity function inside sp function. So you can check up with that, because this is very good for those of you in civil engineering where you need to use equations, and then you integrate your sh with respect to x, and then when you say do it, it will perform the integration. Okay, so all that we have done, you will find them here. So these are the equations, and then this is the bending moment equation. So you get that, and then now to plot, you will now define your lane space, because we are giving values from between minus 0.1. Okay, we are giving values from minus 0.0001 to 10. So now we are building up on that, and we're trying to derive about 1000 values in between. So now whatever you do here, you append it into this SF, and then for the beam, also beam balance, you also moment of the new substitute x of x with that of I, and then you run everything comes into line 13 here. So when you plot your x values and the XSF, you get this color by default, and you plot the second one, you get this color blue by default. Okay, so you can change the colors. You see the beam balance and the surface. Okay, you can change the balance, the color. You get this. Okay, all these ones are just Matplotlib manipulations. Computations are already done. So the same thing, you can look at loading conditions, P of K, and you can separate them. The shear force diagram, you can also look at them, and then the bending moment diagram, you can plot them singularly this way. Okay, so at this point, I want to thank you very much for joining me in this class. Please don't forget to share, like, and subscribe. Please follow me for more. I wish you all the best, and thank you very much for the opportunity to show you this stuff. Have a nice day, and bye.